I'll start again. Today, I'll talk about distance-based classifier with a quantum interference circuit. A large share of the suggested quantum machine learning algorithms are based on the assumption of a large-scale universal quantum computer that can implement non-trivial circuit. This is specifically true for distance-based machine learning models. Quantum algorithms for k-nearest neighbor and clustering have been based on extensions of amplitude amplification, while quantum kernel methods such as support vector machines and Gaussian processes rely on the rather technical routines for quantum matrix inversion or density matrix exponentiation. Experimental implementations are necessarily limited to demonstrations that concede a best reduction in complexity of the quantum circuits. So instead of choosing a textbook machine learning algorithm and asking how to run it on a quantum computer, let's turn the question around and ask what classifier can be realized by a minimum quantum circuit. In this paper, the basic idea is to use quantum interference to evaluate the distance measure of a kernel classifier in quantum parallel. Let's consider the task of supervised binary pattern classification, which has dataset shaped like this. Then the task is finding a label of new unlabeled data. The classifier effectively implemented by the quantum interference circuit together with a thresholding function is given by this equation. The distance measure be interpreted as a kernel and is in fact very similar to an Epanikov kernel. The quantum machine learning algorithm that implements the classifier from this classifying equation is based on the idea to encode the input features into the amplitudes of a quantum system and manipulate them through quantum gates, which is called amplitude encoding. Using a stable state preparation scheme, the quantum classification circuit takes a quantum system of n qubits in state D. Here, M is an index register and flagging the nth training input. The second register is a single ancilla qubit who is entangled with the third register encoding the nth training state and the new input. The fourth register is a single qubit, which is 0 if label is -1 and 1 if label is 1. Normalization constant C depends on the preprocessing of data, and let's assume C equals 1. After state preparation, the quantum circuit only consists of 3 operations. First, a Hadamard gate on the ancilla interferes the copies of the new input and the training inputs. The second operation is a conditional measurement selecting the branch with the ancilla is state 0. This post-selection succeeds with this probability. The state when the post-selection is successful is as follows. In this state, the probability of measuring the class qubit ym in state 0 reflects the probability of predicting class -1 for the new input. The choice of the normalized feature vectors ensures that third equation and choosing the class with a higher probability therefore implements the classifier equation. Last equation is because of the data is normalized. In this paper, interference circuit has implemented with the IBM quantum experience using the IRIS dataset. Data preprocessing consists of 2 steps. First, standardize the dataset to have 0 mean and unit variance. Second, normalize each feature vector to unit length. And this paper used data to testing. Training data 0, 1 and new input x tilde. This figure is a quantum circuit implementing the distance-based classifier using the 2 training vectors x0 and x1 and the input vector x tilde from the rescaled and normalized iris flower dataset. First, step A, Angela and index qubits are put into uniform proportion. Step B, the input vector x tilde is entangled with the ground state of the Angela. Step C and D, the training vector x1 is entangled with the excited state of the Angela and the ground state of the index qubit, followed by entangling training vector x1 with the excited state of the Angela and the index qubit. Step E, the data and class qubits are swapped and the class qubit is flipped, conditioned on the index qubit being 1, which completes the initial state preparation. Step F, Hadamard gate interfers the copies of x tilde with the training vectors, and the ancilla is measured, followed by a measurement of the class qubit when the ancilla was found to be in the zero state. So ABCDE is ABCDE are state preparation step, and F is algorithm that I talked earlier. So that is all. The results show that running the quantum classifier circuit on the entire data set for classes 1 and 2, as well as for 1 and 3 of iris species, results in a 100% success rate, while distinguishing classes 2 and 3 only yields a 93% average success rate. This is due to the fact that classes 2 and 3 are not linear separable and cannot be distinguished easily by distance-based method. The circle dataset is not suitable for a distance-based classifier because 2 points in same class could be far than 2 points in different classes. However, by using 2 copies of the quantum states that represent feature vectors, one can implement polynomial feature maps that increase the power of the classifier. This is end of my presentation. Thank you. Any questions?
I have one general question about QAnon. So,
Yeah.
what is the role of index register in QAnon? Because for classical machine learning, we don't care about index register.
I think it is because of entanglement. Without in this case, I think it needs the index register because to use amplitude encoding, I think, to represent that states. Or are you meaning register M?
Yeah, I was just like a small m. I was asking like, what's the purpose of small m, like index QB? Because like classical machine learning algorithms like don't require like indexing. So I was just curious about like the difference between like QML and classical machine learning in terms of the index QB.
I think in this case, we need that to select the state which is ym label equals 0. If we don't use it, I think it is hard to making this state. Second one.
Using this compared to classical approaches in terms of
Purpose of this paper is not improving time complexity. That's not purpose of this paper. This paper is just to implementing distance-based classifier algorithm on quantum computer. So Arthur doesn't mention about the advantage of this algorithm. Yeah. It made maybe 5 years ago. So yeah, it is not for performance, just one of methodology.
Sorry, but I don't have a preliminary knowledge of this paper, so but can you show me the first paper, first slide of this paper? Can you introduce what is the distance-based classifier? for
Oh, uh, if you should this in this equation, we predict the label of unseen data x tilde by that equation, kinds of threshold function. Uh, yeah,
We know y and x, y and x, right?
yeah,
We know data, and
yeah.
we want to extract the data from y and x, and the extracted data is x tilde, right?
X tilde is new input to which we have to predict the label.
Ah,
Yeah, like this. XMs and YMs are training data set, and we have to predict label of X tilde.
okay. Okay, but that I don't know about machine learning.
It's just binary classification. By using this data set, we have to predict label is -1 or 1 of this new input. So, and then we could use this equation to predict the label. And in this equation, there are some formula similar to distance, x tilde minus xm square. So this because why we call it distance-based classifier. And this paper is about implementing that equation on quantum computer.
Can you show us the quantum safety in the last part, what it's doing?
I mentioned that this algorithm is constructed of 3 parts. First, Hadamard scale on Anchala, and second, conditional measurement, and finally, choosing the class with a higher probability. And here, the after F part, first Hadamard gate is this step, and second one is this conditional measurement, and finally, we could know the label by distance-based classifier.
So the purpose of the conditional measurement. So if you get certain result from that measurement to measure the other register, or you just leave it.
That conditional measurement is for making this state. To implement that distance-based classifier, we have to make this state, and we can make it by conditional measurement and just choosing the state which has this qubit is 0. Yeah, just selecting this part by measurement.
So you take the value of the second measurement in your like inference or in your like financial stuff.
Yeah. It's just making that state, and the probability is probability to get that state from this state. Yeah, so F part is all of algorithm. Other are just preparation. Yeah.
I think I understood, but can you explain what quantum interference is? Like you mentioned on the-
Oh,
yeah, quantum interference is like how is it interference? Interference.
I'm not sure.
Interference.
Mm,
Is it like the title of the paper?
yeah, I just copy and pasted it.
Maybe a first,
But really classification function is also called inference function.
Hmm.
So in the context of machine learning,
maybe some inference like
so you inference is like yes.
by is the phenomena maybe they use interference to show like the still just measuring it was two and just thought it was it's not really the condition. Yes, it's yeah, I mean, I was just wondering why I was called interference.
Okay, really quick. Well, do you have more questions?
Maybe if they would be.
Ah.
I think what's the difference between like quantum classifier and the classical classifier using KNN in classical machine learning and using the quantum classifier? What is exactly the difference between the two? And is there any like changes when you're using the quantum classifier? I don't know, it's QNN or something like I don't know what you call it, but what's the advantage when you're using QNN? And when you're using KNN?
Second question was advantage of using KNN, and can you repeat the first question?
What exactly the difference between the quantum classifier and classical classifier in machine learning?
Difference between them? Their concepts are same. They are all based on the threshold equation, and the difference is just how to implement.
How exactly you implement this one? When you're using the quantum computer, because in classical machine learning, you have the training data, then you input the training data to get the output, like you say, the binary, then you get like the one that you want to get the data, like the sub data, the IUs data. How about in here, like what kind of thing you are using it quantum?
In classical version, we can just calculate this equation, and quantum version, this was implemented by that F part. So this is main difference of implementing and advantage of about second question. QNN and KNN are very different algorithm. QNN is one of neural network using quantum circuit, using lots of circuit, and so making more complex gates. So that is QNN, and KNN is one of clustering algorithm. So yeah, they are different algorithms.
Are you referring to 2 years later?
Q nearest neighbor.
The quantum version of KNN.
Oh.
I mean, this is
Sorry, I don't know the exact implementation of Q nearest neighbor.
I didn't read it,
Yeah,
but I guess the target between this one and nearest neighbor are any other questions? No? Okay, and thank you for the presentation.
yeah, thank you.
Next week.